Hey guys, how's it going? Back again for Python BACnet Stacks Playground. Just want to do a little bit of updates for, I think this is also kind of like the Open-FDD Dev Log series. Just some updates. I've been working on these Vibe Code 19 and 20 applications that are about trying to recreate like a digital twin for building a physics-based digital twin in Vibe Code App 19. This project was about fault detection, and then it's later going to be built into the Open-FDD itself, because I think it's actually better than what I was trying to do. So okay, so Python BACnet Stacks Playground. Join the Discord server. It's just this button right here, and so Vibe 19. This is the fault detection app. Streamlit. We've talked about that a little bit on the previous video. So Streamlit is a data science dashboarding tool. Easy web app to spin up a dashboard. Good for data scientists and analysts. You don't have to worry about any of like the back end or front end software engineering concepts. And then also this is 520 is this is actually running the EnergyPlus energy simulation tool, and also it's basically a dashboard where AI agents can use the EnergyPlus MCP. And what I'm trying to do, I'll show you guys in a couple minutes, is actually take the outputs of this, so fault detection, HVAC analytics, and then through chatting with the AI agent, um, just about these buildings. It'll kind of give you like we can start spinning up a energy model, which is a physics model of the building, and then you're kind of 2/3 the way to a digital twin. I think, in my opinion, I think the digital twin is very loose terms, and I'm still trying to like wrap my head around what is even useful in a digital twin to a person on their day-to-day basis. But I'm kind of like approaching it from this point that a digital twin would be useful for mega mechanical updates. Part of my work experience was mostly as building automation contracting, some retro commissioning field work in there too for engineering firms, and I did also work for an ESCO, and those are they're performance contractors in the United States, at least they're called that, where they're specialized contractors that go into old buildings. Basically, mostly it's all geared around towards public funded, public owned buildings like federal hospitals, school districts. So they're publicly owned, taxpayer paid. So there's contractors that specialize into going into these old buildings, and then they see things in the building where we can update this mechanical system, we can replace this old chiller, and then the tax-paying community, sometimes it's a school district community, they get the performance contractor pays for the update, and then they slowly get paid over time through savings of the project. It's kind of weird. It's like they're a little bit like they never have a very good reputation. They're kind of meant a lot of like sometimes there can be bad reputation. They're kind of like crooks that they're like, sure, we can give you a brand new roof and windows and brand new HVAC system, mechanical system, and controls, but it'll cost you. They're kind of like a little bit, not the bad word, but they kind of have bad reputations, mostly in my experience. So I've worked for one of those guys, and they, part of what they do is like heavy energy audit experiences where mechanical engineers go into buildings and they build like these huge spreadsheets, dashboards, mostly Microsoft Excel, where it would just be a very mechanical engineer focused fuel use of the building, benchmarking fuel use to other buildings of the same type. A lot of mechanical engineering theory of like they think they can save this amount of energy by the new chiller, return on investments. Yeah, heavily ASHRAE level 3 or something, energy audit focused. Um, so, anyways, like that's where I'm going with this digital twin. It's kind of like um, probably something more useful towards that. I just remembered. Hopefully, my sound is. I just forgot to just make sure. I have all these problems with the microphone on this computer here, which I really apologize for. Down to 59%. Hopefully, hopefully the beginning of this video was not super quiet, which I apologize for. Anyways, um, so updates for Vibe 19, fall detection, HVAC analytics. We dump that output into a different Streamlit app. And then this is, I'm just using Cursor, my AI IDE environment. That's just going nuts, revising the EnergyPlus energy simulation. And there's another thing worth showing you here too, is everyone knows about ASHRAE guideline 36, which is the high performance sequences, but there's many guidelines. Guideline 14. Um, okay, so like guideline 14 is if I get something good. Okay, so guideline 14 is all about measurement of energy demand and savings. So like when you spin up uh, an energy calibrated model from an energy simulation tool, um, the results have to be within some certain range of actual fuel use for the building. So that's what guideline 14 is about. I know just enough to be dangerous here. So, Guideline 14 provides guidance for reliability, measurement savings for energy demand and water achieved. It's basically so, like, yeah, here's even the word. The Guideline 14 is intended for transactions between energy service companies, ESCOs, which we're talking about, and their customers. So, when it can't be a crappy model, it has to actually, uh, there has to be model percentage of error between modeled fuel use and actual fuel use. So that's what guideline 14 is, about. And so this Watt lab is kind of, we attempt to build some charts, model some energy plus simulations with the AI agent, and then it has to be within guideline 14 compliant, which I can't do figure it out yet. So I know just enough to be dangerous here. Let's just talk about some certifications. So certifications. At one point in time, I have this one, Certified Measurement Verification Professional, Certified Energy Manager Professional. Um, I have Building Commissioning. What else do they have here? They do have something in building simulations too. Certified Industrial Energy Professional, um, Lighting, Auditor. So Energy Services and Commissioning, Energy Auditor, Building Commissioning, Certified Performance Contracting Funding. Wow. Um, Home Energy. I wonder if they got rid of their building simulation certification, Certified Water. This would be a really good one to have in the future. I would almost consider getting a certified water efficiency professional, just because water is like the next oil some people talk about, is fighting for fresh water. Um, Solar, green, carbon auditing, sustainability development, renewable, utility service, demand side manager. That would be really cool. Um, Certified procurement, Those are people that are brokers, energy marketing professionals. I don't see their one about, unless I'm just missing it here. I don't see the one about energy simulation. Maybe they don't have it anymore. But ASHRAE does have one called up a BEMP, BEMP. That's a certified energy simulation person. So this would be the type of I should like go for this in the future. Like if I do more work in this path, it's kind of fun. Um, I need to be a little bit better at this. It's a world, I swear. So people that are HVAC design engineers, they're like they naturally use the tools to size HVAC systems, and some of them even have building energy simulation and the HVAC sizing features built into the tool. So, like if you were a train trace simulation tool, I've never used train trace before, but um, this is kind of something that it's not free, but you can actually size the mechanical system and you can simulate the fuel use of the building too. You can calibrate the model. So Carrier has one too. Carrier, let's see, Carrier HVAC simulation and sizing. Well, I've used this back in the on a HAP. Um, I've never used this professionally, but I've used this for coursework, for school coursework. So it's kind of a cool tool. So it's you can simulate the building fuel use, and then like at the moment it's not free though. I don't think EnergyPlus. So we're just using EnergyPlus. Um, this is something pretty widely known, and it's been around forever. And there's yeah, this is what we're using to simulate the fuel use of this building in the Upper Midwest. EnergyPlus, and it's maintained by NREL. So like, I'm just pulling a Docker container for EnergyPlus from I'm not actually doing this. The AI agent is doing this, so it's just pulling Docker image from NREL, publishes it to Docker Hub, and then we're also playing around with the AI agent is playing with EnergyPlus model context protocol. So this is from I think it's from LBNL. So NREL makes the EnergyPlus, which is a huge physics engine. It's probably been around for 20 years, I don't know. But it's all built in C and C++, compiled application. And then this model context protocol thing that's not that old, since AI, one contributor, Python, 17% Python. So looks like there's Python behind the scenes. So the AI agent uses this to try and dial in this energy simulation to guideline 14. Okay, so let me just show you like what we got here so far. Oh yeah, here's some big ladders. Maybe I should do some more of this stuff. So they have like upcoming workshops for EnergyPlus, and I know just enough to be dangerous in here, and I should be doing more work in EnergyPlus. There are some HVAC designers. There are, I think EnergyPlus is taught in academia too. Cause so like, I've seen some architectural engineering students, mechanical engineering students, graduate level, where their graduate coursework is focused in building simulations, and they're really good at this. They're way better than I am, and they're really good at the statistics and um, statistician side of things. So I've seen some like really smart um, graduate level students that can run circles around me in this type of thing. And it has like a lot of like HVAC design. If you're an HVAC designer, you're like 95%, this is your wheelhouse. I don't really have either of those backgrounds, so some coursework though over the years. Okay, so let's go back into this is the Vibe 19. So Python BACnet Stack. Oh, this is Vibe 20. Python BACnet Stacks Playground. Come on, words. This is Open-FDD Lab. I'm going to show you this now. At some point in time, both of these will be morphed into the Open-FDD tool someday. Okay, so we're in the Lab studio here, and I have these. So we have been talking about these two. Let me just bring up this picture. Last couple videos, like we've been talking about two buildings, Upper Midwest. There has been some. I've shown some screenshots of the BAS building automation, air handling units, big fan systems, huge office buildings with lots of glass. I'm trying to keep this building like a little bit anonymous. So you just so they're two twin buildings. This is just like an artistic render of it. Two twin 140,000 square feet of conditioned office space and conditioned office space. I gotta wait to zoom in on this. Maybe I'll just download it. The download button. So this is, yeah, kind of, not too different in the real world. They're built in the 1980s, 6 floors. I am using this, so you have to enter parameters. AI agent is doing all this for me. And we're iterating across actual fuel records and trying to make a simulation of the building fuel use. So lots of glass, just like it is in the real world. I'm using a wall to glass ratio of 75%, which is very high. And let me just think. The thing that's kind of weird about it is like these two buildings in the real world, they have a single electrical meter, which makes it kind of hard. But then they have split gas meters. So boiler systems in between the two, separate boiler systems, completely separate HVAC systems, but they're identical. So hot water boiler system in each, where they're low, high efficiency boilers, not high efficiency boilers. So 80% or less natural gas usage, and yeah, I think I mentioned, yeah, in two air handling units, two big fan systems. Last couple videos, like fans around 80, 90 horsepower, 100 horsepower fans. So big fans designed in the 80s, which I think is kind of common in that, because I remember southern Wisconsin area and some of the buildings I've worked on about the same vintage, seeing 100 horsepower variable volume air handling unit systems that would push air, entire office building like this, all 6 floors. So maybe that's just a common design at the time, where it seems like nowadays you'd have smaller packaged air handling units, perhaps on each floor, versus one massive one or two massive ones that push air around the whole building. And they do have water cooled chiller systems. And a really hard thing about this too is there's like very little or no data about the architectural So that's where, like, if you were a mechanical engineer that designed HVAC systems, when you need to make assumptions about the building, um, that's where your design expertise and experience comes in hand, which I don't have that experience. I've been all on the commissioning, field work, and controls automation, sequencing of things. But that's where like they can, when records are missing, lots of assumptions are made to build the model, and yeah, they go off of that prior work experience. Okay, so I think we covered that. Okay, so right now we're in Vibe 20. I uploaded a document about fuel use and the um yeah, let's see. So these are just monthly fuel records, and then this is just another zip file of um oh yeah, no, these are outputs from Vibe 19. So like I'll demonstrate this on another video, but you can output the analytics. Just show you that real quick. So I haven't been able to just do one building. Talked about this building 100 quite a bit. Um, Load the zip file. Great, the little triathlon guy on top is spinning around. I have to close my mouse thing, open it again. Oops, highlighter. Okay, so little triathlon guy is running his race. So right now what it is doing is crunching all of the numbers. And then there's also like this export button. So I won't go into too much detail here, but there is like an export button that exports all of the run analytics of the HVAC system that can be used by the AI agent on Vibe 20 to um, tune the model to actual HVAC operation it'll attempt. So, like fan run hours per week, set points, that kind of thing. So you can like see that in the model. So we talked about this a lot on prior videos. So it's some of the run hours, that can be useful when doing the analysis, like when the chiller runs and everything like that. It's referenced some of the other videos if you want to see the fault detection stuff. Just want to check this export feature. I'm working on stuff too where AI agent can um, build like a fault detection report for you that's coming. So this is like the Watt Lab dump right here. And then this is all of the building HVAC data from the control system. Okay, so these are both uploaded to this building. Now I'm on the Vibe 20 application. Let's go to a fuel use dashboard. Okay, so fuel use dashboard is kind of ESCO style, which we talked about. So campus fuel use, this is in kBTU per square foot. There might need to be some metric conversion. Maybe I'll make note of that. And then to have like a metric switch button down here for metric units. These should be in per year. So it's basically, you can switch between different kinds of school or different kinds of building type. And basically for office building of this size and nature and location, we should be at 52.9 kBTU per square foot, but these buildings do run a little bit higher on the fuel use footprint. And you can see that in one of the buildings, we're at 66.9, and then this guy is outside of the typical range, the 100 building. So this dashed line right here, the green one, that would be this average number. And then if you're within the green range right here, that would be within the 20th and 80th percentiles. But the 50 building is, and then the other building is not. So like, I could probably ask the client what would cause that. And I'm curious if it's because of occupant loads or updates. I think that this building might have had a chiller upgrade. So something like that could do it too, where if this guy is running the original chiller, maybe a newer one, slightly more efficient, could be slightly better fuel use. Okay, so like this is a heat map for kBTU per square foot per year. It looks like just by going off of the most red, 2020 was their worst. And you can kind of see COVID in here too, I'm guessing, where it's kind of lighter. And then we're really back on the occupancy track. People going back to work in 2025. So I bet that it could be plug loads between here. Makes me think about that. We could even attempt to estimate that just by COVID. No one was here. What could have natural gas looks like it really drops off in the summer and most intense in the winter months, which is expected. Worst years being in 2018. Here's some charts basically of that same information. Then if we go to the monthly utility analytics, there's this monthly comparison. Gas, it's a time series chart. Looks pretty normal to me. And we saw that those earlier years were the worst, 2018. Rolling average of the EUI, Energy Use Index, kBTU per square foot. And you can kind of see some general trends. I guess COVID was here. We could make some assumptions for plug loads, which I mentioned there too. And then this is just some of the data people could download if they wanted to. Okay, and then we also have a feature in here too to fetch data from Open-Medio. That is the free weather service at the moment where you can grab data from the internet, historical data, which has not been very easy to do. And this is basically builds model of the data. It's a regression model against cooling degree days. This is actually natural gas model. It's right here, and then the electrical model is here. Just this really simple models for cooling degree days for electrical usage, and heating degree days for gas. Gas has a pretty strong typical model, and electricity not so much, but you can kind of get the idea. Okay, so then you can even trim down the usage too. So like if you wanted to make different models. So this is all 9 years of data, which really common is the statisticians is that they play around with modeling. Maybe you don't want all 9 years of data to make models. And it's actually, if I dial this back, this model gets way better on the R squared with less data. So people like play around with creating models and even just 2 years of data. So I think you get my point. And then this is like what we're trying to dial in the physics simulation, which I'll show you in a second. So this is demand. Um, Demand right here. This 2018 year seemed to be the highest fuel use for electrical and gas and demand. But it seems pretty predictable, at least for this building 100. So when peak demand hit, not too much difference. Must have been summer months. Yeah, very, average daily max temperature on this side was upper 70s, so degrees Fahrenheit. So nothing too different here. Not even during the COVID years, the demand was not too terribly different than non-COVID years. So like last year, 2025, 819 kW versus COVID years of 732. So maybe we could even benchmark plug loads off of that too. Just guessing here. So like that's about 90 kW difference, where I'll have to do some research on this to see if about 50 to 60 kW, not only in plug loads, but this could also be in the amount of electricity it takes to cool humans, which the mechanical design engineers, they add all these loads up. So not only is it like to cool humans, give off heat, lighting gives off heat, computers give off heat, um, solar gains. And then there could also be factoring in here too, maybe even these could have even been the original T8 fluorescent lights, and then all of a sudden down over here, maybe we got a switch to LED lighting over the years, and even that can make significant differences in the building for cooling loads. Just switching out the lights could have an impact, so there's a whole bunch of things going on behind the scenes here that we could not be perhaps not seeing. There's a data quality button, and we don't have any interval analytics or costs or anything like that. Okay, so what I want to get into next is this is the calibrating the model. Okay, so we saw this before. This guy's at 71.6. So these are all the different simulations that I've ran. There's been, wait, sorry, we need to get down here a little bit. Oh, look at this. So we did actually, the AI agent did actually get to, I iterated enough that it fit a model. Huh, okay, I haven't seen this yet. So this is all built by the agent. This is actually a JSON. It saves data in the form of a JSON file, like a pretty decent sized one. And then when we refresh the browser, this is how I see this data on this UI. Okay, so let's get into this. Okay, so like this is kind of the biggest thing to talk about, and then maybe we can chat with the agent too. Let's full screen this. Okay, so this is my iterations on the model. So I had to force the agent like to as soon as I Googled enough information about the on the internet about these buildings, glazing type and do create these different the words I'm trying to use. It's basically like the geometry of the building. So like the uh, building energy simulation people, like you have to dial in the geometry of the building, the actual length, height, width of, and then you can really get into architectural components of the building, U values, R values of windows, window frames, siding, and then you can even like attempt to guess what the energy score, what the energy, like ASHRAE 90.1 is all about energy code requirements. What was it in the 1980s? What have they done over the years to maybe bring that up to the 1990s code requirements for so there's all these assumptions we don't know about the building. And so these are iterations that the AI agent has done to dial in the building to actual fuel use. And what's kind of confusing here too is uh, there are two buildings, two twin buildings on the same electrical meter, so you have to keep in that mind too. Okay, so this line right here, this dashed line, that is the guideline 14 root mean squared error. And then this is also the other gate for model has to be within 5%. So both, you can see like up here, this is the gas. So trying to dial in the geometry, the loss characteristics of the building, all these different features of like maybe they run the building longer at certain hours of the year and they don't on certain, so there's all these assumptions. Some of the data from the Vibe 19 app output helps of like because it can make a big difference in the fuel use if the if there's 0% outside air during the hottest and coldest months of the year. By the way they operate the building, which we talked about in prior videos, all these little things, they add up. Um, so like I was basically pushing the agent through here to keep on dialing in so glass to wall ratios, and then also the R and the U value of the windows as well. So like that's the loss. Um, Oops. So let's just get out of close full screen. Okay, so this is like our little sim of the building. There's two of these in mind. Keep that in mind. We only see one. 8760. So this is just kind of like some of the characteristics that you would see in an energy model. This is the output from EnergyPlus. And seem to be missing a chart in here. We should see a chart per we should see a chart in here. So I'm not seeing it at the moment, but it's per month that the records were off. Okay, so let's just look at some of that. This is some of the stuff I've done chatting with the AI agent. Okay, so the AI agent finally did guideline 14 pass on the first month aware. And we were talking about that the model over predicts electrical and gas usage during peak in summer. Okay, so seasonal light. So the May through June peaks down. October, November, August peaks up. June electricity. So like the model was basically over predicting on some months of the year and under predicting on others. But we got to a point of being able to pass for guideline 14. I had to push this AI agent quite a bit. Okay, so they're failing for different months patterns. Godling 14 needs both this 5% air gate and this root mean squeed air on each fuel. So I could get the gas to pass, but then electricity was unusually high, or vice versa. And you play around with like different loads in the building and different, yeah, so basically, what we got here? Okay, so like on this particular model is like the patterns would cause the model was too high in shoulder seasons, basically. It would 26% of what actual usage was, and what was going on is cooling plus high internals was causing high prediction, I guess, and then it was too low in October, August, and November. Okay, so there's, yeah, and I think like some of these like people that have whole work experiences in HVAC design, you know, like they can do so much, like a lot better job than like what I can do. But like what's kind of fun doing this exercise to me is like the AI agent is like building itself tools to do this. So like I'm documenting all of these, you know, it's writing Python scripts to modify the EnergyPlus model, look at some of the data from the analytics from 519, and then it's even building itself a little AI agent skills calibration, you know, what it did. So I think it's doing some cool stuff. So I'm like, this stuff I am documenting. And so let's just ask it like, you know, can you summarize a nice paragraph how you dialed it in? What did you learn? So I have to ask it, this video is turning out to be kind of long. But then I also have to ask it to, maybe we can go over this tomorrow, but better fault detection reporting from 519. Okay, so let's just read this. So I'll zoom in just one more notch. Okay. So we dialed in building 100 in layers, not by chasing plant tons. EnergyPlus stayed auto-sized. So that's another thing too, is like you can, EnergyPlus can auto-size the HVAC system, or if you know, if you have really good records of the building, you could just enter in the plant capacities for the chiller, the tower, pumps, fan sizes, and everything, but we don't know that stuff. So the work was geometry, envelope, and then as operated HVAC. That would be from 519. Then month aware loads. As we locked in the real twin, the 6 floors stacked together, not the DOE. Yeah, okay, so we had a better model of the building. Then closed the annual gas shortage by raising the window to wall ratio to 75%, leaker glass, and infiltration until gas was roughly flat year round while electric stayed near the bills. That annual win still failed on gas. So as soon as we fixed electric, then gas would get screwed up again, you know, vice versa. Winter high, summer empty, 519 HU data pointed, you know, a 50-degree discharge temp during the summer months, which is causing, which would cause heavy natural gas usage in the summer for reheat purposes. So we banded supplier temperature and flow. Yeah, so it's basically what helped us is like some of the records from the 519, which will also be an ECM coming up on this video series. We'll try and use this calibrated model to put together a report of energy saving ideas. And some of these will be high level design ideas, like what they do in ESCOs is uh, they can estimate what it would take to, like a building like this, to add updated mechanicals. I want to add updated like energy recovery. So we'll be able to do this as an ECM in this tool. And then this is also an ECM too, causing heavy reheat. So basically what's happening in the building that we tuned the AI agent was able to dial in the gas usage a little bit was 50-degree leaving air temp from the air handling unit to probably meet one or two critical zones causes heavy gas usage to make that up that difference. So I think that's an ECM opportunity and like it would be a major mechanical update though. Um, so we'll be able to kind of have like a pretend redesign of the building, virtual one, simulate its fuel usage, and then make uh, return on investment um, decisions on this too. So it's coming, and this is pretty. So there are people that do this is what they do for a living. I'm just using AI to iterate across this. So, but this is just common mechanical engineer workflows in ESCO industry where they're heavy energy audit. This is like the full ASHRAE level 3 kind of calibrated energy simulation. So there are people that do this for a living all day, every day, and they're probably way better than I am. But we're just using AI agents here to facilitate what they do. Um, okay, so that was one way how we dialed in the natural gas usage, still holding at 50 degrees all spring, but blue part in October. Starve. Okay, so what I figured out is breakthrough for gas and to meet guideline 14 was seasonal outside air. Starve. January eventually cut off. So basically, I think like what they're doing, this is good because this is what they do, how they operate the building, which we saw in the analytics is like during times of weather extremes, they close the outside air dampers, put the air handler into a return air mode, which I think in the simulation we were able to use that in the simulation tool here. Pretty cool. I think this is neat that the AI agent was able to dial this in, but it took a ton to dial this in too. Um, like I pushed it for days, push it. Even asked some of my former coworkers, how would tips from them too, which I dumped into the AI agent to keep on iterating. Okay, so calibrate in order. We did the geometry, envelope gains. Then we shaped monthly evidence, and then when I was pushing the agent, it was these knobs we were turning. Keep on turning up the infiltration. Keep on turning up the U value on these crappy old windows from the 80s until we could eventually kind of I would tell the agent to do 5 aggressive iterations, and keep on getting slightly better numbers, and do 5 more, and do 5 more, and keep going, and it did it. It found it. It's like the real cool thing would be for a person that is like a certified simulation expert, get their lot once over on this, anyways. So I think I have to stop it here. The next video, maybe tomorrow, we will go into the better fault detection outputs from Vibe 20 or from Vibe 19, which I want to show you guys. Fault detection reports, and then we can go start getting into this ECM tab here. So like I do have some pre-built energy savings opportunities. So we'll be working on this tomorrow. So in I do have some data from ChatGPT, um, putting ChatGPT into um, advanced, into deep research mode. And like, so like what the energy audit people do and the energy calculation people is they have benchmark scripts on like physics calculations, like this building should be within this kBTU, this fan, if we did an ECM and a saving strategy, it should save about this couple different um, so we'll get into that tomorrow. You can even ask ChatGPT to make an Excel spreadsheet for you too. So based on a 100 horsepower fan, if we did a guideline 36 duct static pressure reset, dialed back the fan usage, what would that save you in an Excel spreadsheet style? And then we can compare that to the energy simulation results. So that's the most important thing. It's like we're comparing um, spreadsheet calculations to calibrated physics energy simulation model in EnergyPlus, making sure we're within kind of healthy guidelines and limits. So, okay, so this is all I should do for today. Hopefully my microphone is working, and I'll see you guys tomorrow. We can get into some of the ECMs. I'm also writing part of this. I'm just going to log into LinkedIn real quick too. This will be part of a um, this will be part of an article. So I wrote um, article how to build a digital physics-based digital twin, which Vibe 19 is this, and then I'm almost done with Vibe app 20, which was part 2 right here. And yes, and then this will be coming soon too. This will be tying in. This will be a Unity in Unity too. So this will be part of the digital twin in Unity. So throwing a lot out here. So thanks, guys. I will see you tomorrow.